Okay? Now, let's look at each of these statements together. So basically, this is related to what we covered on Monday. Okay? So here what we have is if the k difference of yt is stationary, yt must be integrated of order k. Now, is this true or false? Okay, think carefully, what does it mean by being integrated, and what does it imply by the order of integration? Okay? So, this is actually a false statement. Okay? So, the key or the main reason here is that, okay, the order of integration is the number of times we require to achieve stationarity. So essentially, it's the minimum number of times that we should difference yt. Okay? So if we over difference the underlying series, we might still get a stationary time series, but that does not give us the correct order of integration. So to see this, okay, let's look at our familiar example, the random walk with the drift. Now, we know that if we difference once, okay, so if we subtract yt minus 1 on both sides of the equation, then on the on the left, we get the first difference, the delta yt, okay? And on the right-hand side, the immediate lag canceled out with itself, and what is left is just the alpha naught plus ut, okay? And we know that this first difference is stationary, given that ut is a white noise, okay? So the delta yt is stationary. Now, what happens if we difference it one more time? Okay, imagine we subtract the delta yt minus 1, okay, and we subtract it on the right-hand side as well, which essentially will just bring in its equation, okay? So we know that the delta yt minus 1, given that delta yt is just a function of the intercept alpha naught and the shock happening at the same time period, then delta yt minus 1 is just alpha naught plus ut minus 1. Okay? Then this implies what we get on the left is the second difference, okay, which is the difference between delta yt and its immediate lag. And on the right-hand side, what do we get? Okay, so we have alpha naught plus ut minus the alpha naught plus ut minus 1. So the common intercept cancels out. Yet we are left with ut and its past. Then essentially we have an MA1 here. Okay, this is an MA1. MA of finite order is always stationary, which implies the second difference of yt is also stationary. Okay, but we know that the random walk with a drift is integrated of order 1. It's not integrated of order 2, because it only needs to be differenced once to achieve stationarity. Okay, so this is a false statement. We need the the order of integration to be the minimum number of times, okay, to difference the time series to achieve stationarity. So if the statement here were instead, okay, if the k difference of yt is stationary and it is the minimum order of difference to make yt stationary, then yt must be integrated of order k. Okay? So what we have here on the Padlet is a false statement. Now, the second one. If a time series is different stationary, it cannot be transformed into a stationary series by removing a deterministic trend, okay? So for those of you who just come in, I'll give you 5 seconds to scan it. Now think carefully. It's Monday, we mentioned that we can make a trend stationary time series stationary by differencing. It's just that differencing is not the optimal detrend technique for a deterministic only model. Here, we are looking at a different stationary process. And the question is, if instead of differencing, we directly subtract the deterministic trend, can we make such a series stationary? Okay. And, okay, we have quite a balanced vote. The answer is no. Okay. We cannot make a different stationary time series stationary by simply removing the deterministic trend. This, again, can be illustrated using the random walk with the drift. Okay? So if we look at the random walk with the drift, and remember, by recursively substituting the equation backward, we'll get alpha naught times t plus the initial observation y naught plus the sum of all the shocks between time 1 up to time t. So the random walk with a drift has both the stochastic trend component, okay, basically given by the random walk, and we also have a deterministic trend component, essentially induced by including the drift. Then, can we simply make the random walk with the drift stationary by subtracting the deterministic trend? Imagine if we take yt minus alpha naught times t, okay? Essentially bringing the deterministic trend to the left-hand side. Then what is left on the right is the initial observation, yet we still have the random walk, okay? The stochastic trend still remains after we subtracting the deterministic trend, okay? So this is not stationary because of the presence of the random walk component, the stochastic trend, okay? Therefore, if a time series is different stationary, the only way we can make it stationary is by differencing, okay? In contrast, if a time series is trend stationary, which means it only has a deterministic trend, then we can achieve stationarity also through differencing. It's just that such a technique to remove the trend is not optimal, and we prefer directly subtracting the deterministic trend for something that is trend stationary. Okay, so this is a this is a true statement. If a time series is different stationary, it cannot be transformed into a stationary series by removing a deterministic trend. Okay, this is correct. Sorry for overlooking the cannot. Now, the last one. If yt follows an ARP, but its phase difference follows an ARP minus 1, this must imply yt has a unit root. Okay, again, this is something related to what we discussed on Monday. Okay, and the majority wins. Okay, this is a correct statement. Remember on the slides, okay, we have that some useful facts about AR1 model. Okay. And what we have is, if the phase difference follows an ARP minus 1, this means yt is an ARP with at least one unit root. And again, okay, I will give an illustration here. for an AR2. So essentially the claim here is if the YT follows an AR2, but the first difference follows an ARP minus 1, which is 2 minus 1, that is 1, then this implies YT must have a unit root. Then essentially this is asking whether when we write YT as an AR2 and we can write its first difference as an AR1, does this imply the sum of the autoregressive coefficients, the alpha 1 and alpha 2, is being 1? Okay? So to establish the equivalence, first of all, we want to show that these two models are identical under the condition. So to do that, first of all, know that in the first difference, we have the difference on the left-hand side. So to get the first difference as the dependent variable, okay, we subtract YT minus 1 from both sides of the equation. And this makes the equation remains unchanged. Now, observe that in the first difference equation, okay, we don't have the YT minus 2 entering the equation directly, but instead it's included in the delta YT minus 1, which is the difference between YT minus 1 and YT minus 2. So essentially to write the AR2 into a form that looks similar to the first difference AR1, we should pack the second leg into a first difference term. Okay? So essentially, we want it to appear in delta YT minus 1. Then to do this, we simply add and subtract alpha 2 times YT minus 1 to the right-hand side of the equation, and that makes the equation remains unchanged. Now, what we get on the left is the first difference, okay? And we still have the same error term. Now for the YT minus 2, okay, we have it the minus alpha 2 times YT minus 1 minus YT minus 2. Okay, because we have the minus alpha 2 YT minus 1 plus the alpha 2 YT minus 2. Then pack it into the bracket, the sum in front of the YT minus 2. Okay, that becomes, a minus because of the minus. Okay, then essentially what we get is delta YT minus 1 times minus alpha 2. And for the YT minus 1, okay, we have the alpha 1 minus 1 plus alpha 2 as its coefficient. So we get alpha 1 plus alpha 2 minus 1 times YT minus 1. And we still have the same alpha naught in the equation for the delta YT. So to write it out, what we get, we have the first difference on the left plus, for the right-hand side, we have the intercept. We have alpha 1 plus alpha 2 minus 1 times YT minus 1. We have the first difference, immediate lag, and we also have the error term UT. Okay. Now compare this with the AR1 model for the first difference, which we have gamma naught and gamma 1 times the delta YT minus 1 plus UT on the right. Now, one last condition we need to use is that we have the alpha 1 plus alpha 2 minus 1 being 0, okay? Remember, we're asking whether alpha 1 plus alpha 2 is equal to 1. Then this is the same as alpha 1 plus alpha 2 subtracting 1 is 0. So if this is 0, then basically we get rid of the yt minus 1 term. And the equation becomes the first difference on the left, and we have alpha naught minus alpha 2 delta yt minus 1 plus ut on the right. Okay. Essentially, we have the same variable on both sides of the equation. Okay. And with an intercept plus a slope, then this must imply, okay, alpha naught is the same as gamma naught, and that we also have gamma 1 the same as minus alpha 2. So essentially, given the fact that we have a unit root in the original series, the yt, okay, which gives that we have alpha 1 plus alpha 2 equals to 1, then we reduce the first difference to an AR1 model. Okay, this result always holds true. So if yt follows an ARP, its first difference follows an ARP minus 1. This must imply yt has a unit root. Okay, essentially think of it from another way. By differencing yt, we reduce its order by 1. This implies it must have a unit root. Okay, by differencing yt being an AR2 to a first difference being an AR1, the order reduced from 2 to 1, so it implies yt has a unit root. Okay, so these are some quick quiz to check what we have covered on Monday. Now, coming back to where we left. So essentially, we talk about the ADF test. And basically, it's just about testing whether we have a unit root in the original series. And the logic of the ADF test is that we transform the AR1 into an ADF regression, where we have the first difference on the left, and we are testing whether the coefficient, the pi on the yt minus 1, is 0. Basically, this is the same as what we have just established. Okay, so we say that if yt follows an AR2 and the first difference follows an AR1, there must be a unit root in yt. Similarly, what we have here on the slide is that we have yt following an AR1. The first difference is essentially an AR0, because when pi is 0, there is no lag, okay? Yt minus 1 will not appear on the equation for delta yt, okay? So this is essentially the same logic. We are testing whether we can reduce yt following an AR1 to its first difference following an AR0 by testing whether pi is equal to 0, equivalently testing whether alpha 1 is 1. So this is the logic of the test. And then we know that under the null hypothesis, which is essentially pi being 0, we have a stochastic trend, so there is a in yt. And under the alternative, there's no stochastic trend, and we are only interested in a lower-tailed alternative. So you should only reject the null hypothesis if the test statistic is more negative than the critical value. Now, before we look at how to implement the test, so let's just briefly go through why should we transform it to an ADF regression? Okay, what actually is the logic behind this regression? So for here, we have the first difference, and we want to know whether the first difference depends on the lag of yt. Okay, so essentially we want to test whether pi is 0 or whether pi is negative. Now, what does it imply by having a negative pi? So imagine our time series yt, okay, we know that under stationarity, absence of shock, it will just stay on its long run mean. Okay, so it will stay here. And imagine, suppose at yt minus 1, there is a shock hitting the system, making the yt minus 1 deviate from its long run mean. Now, given that we have delta yt equal to pi times yt minus 1 plus ut, absence of shock in the next time period, okay, so ut is equal to 0. With pi being smaller than 0, that basically means the difference between yt and yt minus 1 is negative. So the time series will be pulled back to its long run mean because the next period yt is here. The difference, the delta yt, is indeed negative because yt is smaller than yt minus 1. Okay? And the next time period, the delta yt plus 1, which is equal to pi yt plus the ut plus 1. Okay? Again, absence of shock. And given that pi is negative, the yt minus, or the yt plus 1 must be even smaller than yt, okay? To make the difference negative, okay? Then essentially testing whether pi is, the implication that the pi is being negative is essentially that the time series will be mean reverting. Okay, so under the alternative hypothesis, with a negative pi, the time series itself is correcting for its deviation from the long run mean, regardless of its being above or below the long run mean. Okay, if it's above, then just like what we've seen here, okay, it will be dragged down towards the long run mean. If instead yt minus 1 is here, then it will be dragged above, correcting towards the long run mean. So this is the whole idea of why we want to transform the original AR model to an ADF regression with the first difference as the dependent variable. Okay. Essentially, it's about testing whether we have mean reversion. So this is the logic behind the test. Now, let's consider a practical example. So here I want to test whether there's a unit root in employment, in the unemployment rate. And we can see from the time plot here that there's no observed, obvious long-term trend, but there does appear some random wandering behavior in a sense that it's not frequently fluctuating around some constant mean. So potentially we have random walk characteristic without drift, okay? So without the drift means there's no deterministic trend. And this indicates the possibility of a unit root. But remember, the time plot only gives us a sort of like a first kind of guess of whether the time series is stationary or not, but it's not something that's definite. In order to reach to a definite conclusion, we should run a formal test. Now, if we run the AR1 model without a constant for the unemployment, which is something we've been doing all the time, simply regressing yt on its immediate lag. So this is what we get in R, and we can see that the alpha hat 1 is very close to 1, okay, 0.9998, which sort of hints at non-stationarity. Now, the regression, okay, the t value here, the 200 something, it's not the correct t value for the null hypothesis that we're interested in, okay? So what we have here is that is the t value, it's alpha hat 1 minus 0 divided by the standard error of alpha hat 1. It's for testing whether alpha 1 is statistically significant against its insignificance. But what we are interested in is not that it's 0 or not. We are interested in whether it's equal to 1 or not. So the correct t-statistic should be having alpha hat 1, subtracting 1 in the numerator, divided by the same standard error. And we can see that here, the test statistic is roughly minus 0.033. Okay, so this is how you can test for the unit root test using the original AR1 model. Now, using the associated ADF regression, which essentially we transform it to regressing the first difference on the YT minus 1. And we are interested on the pi, whether it's 0 or not. So the first, if we look at the pi hat, this is very small, minus 0.0012, which sort of aligns with our AR1 model estimate for alpha hat 1. Because remember, the pi is equal to alpha 1 minus 1. Then the pi hat must be equal to alpha hat 1 minus 1, although there might be some rounding errors. Okay. Now, in this ADF regression, the t-value given is the correct one that we should use, because it's essentially testing whether pi hat divided by its standard error is equal to some value. So here we have minus 0.034, very close to what we get from the AR1 model. The minor difference is just due to rounding. Okay? So the t-value is the correct one for our intended hypothesis. However, the p-value is not the correct one, because the p-value calculated using the dynamic linear function assumes the test statistic follows a standard normal under the null hypothesis, which in the case of testing a unit root is incorrect. Okay? So what makes a unit root test different from what we have looked at so far is just its asymptotic distribution. It's just the critical value we need to compare the test statistic against is different. That is the only difference. Okay? So the test statistic follows an ADF distribution, not standard normal, when we're testing the null hypothesis of a unit root. And the distribution will be affected by the model specification, whether we have included a constant, a time trend, or not. So here, we didn't include a constant, we didn't include a time trend, so it's a no constant test. Then the critical value for a no constant test at 5% is minus 1.95, okay? And remember, we should only reject the null hypothesis if the test statistic is more negative than the critical value, which is not the case here, okay? Our test statistic is larger than the critical value. Therefore, we fail to reject the null hypothesis, and we conclude that the unemployment has a unit root. Okay? Now, the critical value associated with the ADF test is on the last page of the semester 2 statistical tables. Okay? And you can see that the t-statistic would depend on whether there's a constant or the trend included in the model equation, and that basically will give us different critical values. So we'll come back to this in a bit, the different specifications. So, okay. So there are essentially 3 different test specifications under the ADF test. All these are about testing the null hypothesis of a unit root. This specification only differs by the alternative hypothesis. Okay, so the first one, which is what we have just seen, is a no constant test. So we don't include a time trend or a constant in the test. And this implies under the alternative hypothesis, the time series is stationary with mean 0. Okay, because there's no intercept. Remember from quiz 2, there's actually one option. If the time series is stationary, a 0 intercept basically means a 0 long run mean. Okay, so here, under the assumption or under the alternative hypothesis, alpha 1 is less than 1 in absolute value, indicating that the time series is stationary. Without the intercept alpha naught, it has mean 0. Okay, so this is the first specification. The next one basically adds a constant to the model. And therefore, under the alternative, it's stationary with a non-zero mean. And that's the only difference. The third specification will add another deterministic component to the test, which is the delta times t, the trend. Now, under the alternative, the time series is no longer stationary, but instead trend stationary. Okay? We still have alpha 1 less than 1 in absolute value, but there is a deterministic trend delta times t. So yt itself is not stationary, but stationary around a trend, which is why it's called trend stationary. So under all three specifications, we test the same null hypothesis of the presence of a stochastic trend or the presence of a unit root, but it's just that the time series has different characteristics under the alternative. And which one to use is not a simple choice, okay? So there are some misspecification concerns. Excluding necessary terms in the test can lead to false conclusion. So which means if a time trend should be included, but we have falsely excluded it, we might arrive at a completely misleading result. And we'll illustrate this on the next slide. However, including unnecessary terms also reduces the test power. Okay? This is because there are more parameters we'll be estimating, and also at the same time we'll be using more negative critical values. We'll see the reason for this after the next slide. Okay? So in any case, excluding necessary terms and including unnecessary terms will lead to a reduction in test power. Okay? So pinning down the correct specification of the test is very important to arrive at an accurate conclusion. So to illustrate the first point, so consider we have a trend stationary AI1, which basically means alpha 1 is less than 1 in absolute value, and that implies pi is negative. Now, what happens if we incorrectly excluded the time trend in the model? So suppose we consider only the constant-only specification, so we only include the alpha naught, but not the delta t in the test. So the first thing we observe is for the pi hat, this is minus 0.0039, which is really close to 0, suggesting alpha 1 is close to 1. Essentially, it's suggesting there is a unit root. And we can also see that the t-statistic for testing the hypothesis of a unit root, which is the t-value given here since we run the ADF regression, that is minus 0.598, okay? This is greater than the critical value associated with the constant-only test at the 5%, which is minus 2.88, okay? So then basically, given our test statistic is not more negative than a critical value, we fail to reject the null of a unit root. However, okay, we know that our underlying time series is trend stationary. If we have correctly included the trend in our test by including the delta times t, the first observation is that the pi hat is now minus 0.242, substantially more negative compared to the case where we have omitted the time trend, which indicates that alpha 1 is potentially less than 1. And we can also see that the t value here is more negative, okay? Now, we have included a time trend, So we need to use the critical value associated with a different test, okay? So instead of using the minus 2.88, we should use the critical value minus 3.43 because that corresponds to the trend inclusive test. Then comparing our test statistic, So comparing our test statistic, which is minus 5.20, with the critical value minus 3.43, it's more negative than that, which suggests we should reject the null hypothesis of a unit root in favor of a trend stationary alternative. Remember, a trend inclusive test, under the alternative, we have trend stationarity. So we see that incorrectly omitting a necessary deterministic term will lead to completely wrong conclusion, okay? So this is the consequence of excluding necessary terms. However, including unnecessary terms also comes with some fault. So just to kind of visualize the graph a bit clearer. So on the time plot here, on the distribution here, we have 4 different distributions. So the dashed line, okay, this one, corresponds to the standard normal. I've listed that there just for comparison, okay? And we know that the standard normal is always symmetric around 0. Now, the 3 ADF test, okay, the first one is the one without drift. So it's the purple line, that is the no drift, which means no constant. The next one, the green, is the one with a constant, so it's a constant only. And we also have the one shifted most towards the left, that is the trend inclusive one, okay? So we can see that compared to the standard normal distribution, the ADF distributions are shifted towards the left and they are positively skewed. They have a long right tail, okay? Or another way to think about the positively skewed is that the mass majority of the distribution actually falls towards the left of the plot, okay? And also we can see that these ADF distribution, they are not centered at 0, but we're testing whether pi is 0 or not. So we have a very skewed distribution. And from this plot, we can see that if we have mistakenly used the standard normal as the distribution under the null when we are testing for a unit root, this will increase the probability of a type 1 error, okay? Just to compare, here, this is the value of the standard normal critical value when testing against a negative alternative, and this is minus 1.64. Whereas for the no constant test, the critical value at 5% is minus 1.95. If we have mistakenly used the minus 1.64, essentially our rejection region, okay, this is larger than our intended 5%, which means we will have a higher chance of committing a type 1 error. Okay. Remember, the 5%, the significance level is essentially the probability of committing a type 1 error. So if we have mistakenly used the standard normal, we risk type 1 error. Now, coming back to what happens if we have mistakenly included unnecessary terms. Okay, so first of all, from the plot, we can see that the more deterministic components we include, okay, the further the distribution is shifted toward the left, which means we're using more and more negative critical values, okay? So first of all, in order to reject the null, we will need a more negative test statistic. So more negative critical value requires the t to be more negative to reject the null. So this is the first requirement. Now, if we have included more terms, the more parameter we have estimated, okay? So the more parameters, the higher the estimation error, the less accurate your estimates will be, which implies a larger standard error. Now, remember the t statistic is essentially pi hat divided by the standard error pi hat. Suppose pi hat remains roughly the same regardless of you included or excluded some deterministic component. The increase in the standard error, okay, will lead to a decrease in the t statistic, which means your test statistic will become smaller in absolute value, okay? And therefore, the combined effect of these two would mean that we'll be less likely to reject the null hypothesis when it's actually incorrect, okay? So including unnecessary terms, which is over-specification, will also reduce the test power. So the next question is, how can we pin down the correct test specification? Okay, so essentially, we want to know some procedure that allows us to pin down the specific test we should use. Then typically, we should follow a general to specific procedure. So we start with the most general test, where we included both the constant and the time trend, okay? And here, we start with testing whether pi is 0. If we reject the null, we stop the test and conclude that yt is trend stationary. This is the slide for today. If we fail to reject the null, then we need to continue to step 2. So here, what we're going to do in step 2 is we will test the joint hypothesis. We want to test whether delta and pi are jointly 0 using an F-test. The F-statistic is constructed in the same way as before, but it's just that we use different critical values. That corresponds to the row 5-3, okay, on the ADF F-statistic critical value table. So it's the last row that you should be referring to when you're doing the test in step 2. So here, basically, conditioning on we fail to reject pi is 0. We want to know whether we should include the time trend. We want to know whether delta is 0 or not, okay? So here, if we reject the null hypothesis, which means we reject the null that they're both 0, but then conditioning on we know the fact that pi is 0, this must indicate delta is different from 0, which means we should keep the trend in the test. So the trend inclusive test is the most accurate one here, okay? And we stop here and conclude that yt has a unit root, and we should include both the trend and constant. However, if we fail to reject the null, basically that means delta is 0, pi is also 0. Given that delta is 0, we should not include the time trend, and we should move downward to a constant-only model by excluding the time trend, okay? And again, at this step, we test whether pi is 0. We test whether there's a unit root. If we reject the null of a unit root, we stop the test and conclude that yt is stationary with a non-zero mean. Otherwise, we continue to test the joint hypothesis whether we should include the intercept along with the pi, okay? And this time, we need to use a different critical value for this F-test because we're testing different hypotheses. So we need to use the phi1 values, which is given in the second row here, okay? that corresponds to constant-only test. We should use this critical value for our step 4. And again, okay, if we reject the null, conditioning on we know that pi is 0, that basically means alpha naught is different from 0. So we should include a constant in the test. We stop here, conclude that yt has a unit root and indicative of constant needed. Otherwise, we continue to step 5. Now, step 5 basically comes from the fact that we have failed to reject the joint hypothesis. Given that pi is 0 and alpha naught is 0, we should take away the constant, so it comes to no constant model. Then here, the only final thing we need to do is to test again whether pi is 0 in this model. If it is different from 0, so if it's smaller than 0, we reject the null, conclude our y is stationary with a 0 mean. Otherwise, we fail to reject the null hypothesis, which means that y has a unit root. Okay, so we follow this general to specific procedure to pin down which test we should use and what is the correct associated, conclusion. So some keynotes here, okay? So we should always stop this procedure at the first rejection of the null hypothesis, okay? Either we reject the null that pi is 0 or we reject the joint hypothesis. Or we reach to the final step, step 5. And in any case, we have non-standard test statistic distribution. Okay, regardless of testing pi is 0 or regardless of testing the joint hypothesis, they do not follow the standard normal distribution or the standard F distribution. Instead, they follow the ADF distribution associated with different tests. And you might have noticed there's also an additional row here, which corresponds to phi 2. Okay, so this phi 2 is intended for the test on this is intended for the so phi 2 is intended for the test of both the delta and the alpha naught are jointly 0. I don't know what's happening here. Okay, now it's back. So the phi 2 is for testing whether pi, the delta, and the alpha naught in the trend inclusive test, all 3 are jointly 0. But we're not interested in this here because we want to gradually remove one deterministic component at once. So this is the general to specific procedure, okay? And this is the example using the unemployment case. I'll leave it for you to go through this. Basically, it's just apply what we have seen on this slide to the unemployment case, why we have arrived at the no constant test. Basically, we just failed to reject the null at every single step, okay? And next Monday, I'll start from here, extending the unit root test to an ARP, and also we'll talk about spurious regression. The very last lecture, next Friday, we'll talk about something that's quite interesting termed Granger causality. That's not the causality in the usual sense, okay? We're still within the descriptive framework. So thanks for coming, have a good weekend, and I will see you guys on Monday.